Okay, so we've looked at minimums and maximums already. Now what we haven't looked at yet is an absolute max and an absolute min. And all that's going to mean is if you have a graph, you may have a place where it hits an absolute high point. You may not, and you may have a place where it hits an absolute low point. Why don't you just sort of draw somewhere in here, maybe up at the top or something kind of like this. Just draw a graph that kind of does something like this. Now let's have an endpoint on that. Let's have an endpoint on that. Okay. So if you look at this thing right here would be called the absolute max. How come? Just because it hits the absolute high point that it's ever going to hit. Okay. This thing right here would be the absolute minimum. It's real simple. That's the absolute low point that you're ever going to hit. Okay. This right here would not be an absolute max. This would be what we either call this a local max, or you can call it a relative max. Okay, and all that means is that's a place where the function changes directions. It increases, then decreases. This would be another local max right there. Okay, and then this right here would be a local min. Okay, this also would be a local min. And then this point right here would also be a local max. Okay, you don't have to write all that down, but what I want you to kind of see on here is what a local max is. What does a graph do when you have a local max? It means to the left it's increasing, right? And then it starts decreasing. That's all that is. So there actually are 1, 2, 3 local maxes on there, but that's the absolute max. That just means that's the highest point it ever achieves. Does that make sense? That's all it is. And then the local minimum, all a local minimum is it's a point on the graph where the graph decreases, changes directions, and starts increasing. But that is the absolute min because it's the lowest it can possibly be. Now you can also have something kind of like this. You could have a graph that might do something kind of like this. Well, that would be an absolute max on an endpoint. You can have an absolute max on an endpoint, and then this would be an absolute min. Okay? These things right here would be local. This would be a local min. That's a local min. That's a local max. That is. But this right here is not a local max. Do you know why? Because a max has to increase, then decrease. There's nothing going on to the left of that. So that is not a local max, and that is not a local min. Okay, does that make sense? Okay, because you've got to have something going on to the left and something going on to the right for it to be a local extrema. Okay, so I'll just kind of explain it that way. This definition is really just saying that you have an absolute max if the function value is bigger than every other point on the graph. That's what that basically is saying right here. Okay, your function value is always bigger than every other point on the graph. A minimum is going to be where every point on the graph, every point, the function value is less than every point on the graph. That's why that's less than, and then that's greater than. That's what that means. Okay, let's look at these graphs. So this just kind of goes through the details of this. So if you had a function y equals x squared from negative infinity to infinity, okay, you have an absolute min. Okay, that's the absolute minimum that it ever hits. You don't have an absolute max because the graph gets higher forever. Okay, that's one possibility. Okay, if you looked at the same function, x squared on 0 to 2, you would have closed points there. Well, the absolute max would be here, and the absolute min would be there. Okay, so absolute min and max can be at endpoints. Okay, all right, so that's another possibility. Okay, let's go to the next page. Okay, now this is where it gets a little picky. Okay, so now I'm doing the same graph, y equals x squared, but notice I'm doing 0, 2. Now, since there's a parenthesis on 0, what does that mean?
It's not included.
It's not included, exactly. So you'd have a bubble there. Okay, that's why. What does the bracket mean? It is included, so we have a solid dot. That's why. Okay, well, this would be an absolute max because it's included, but this would not be an absolute min. So here's why. That is not an absolute min. And the reason is because you're never going to find a point that's the lowest. Like if you used 0.1 on x squared, you'd get a y value. But you would never be able to pinpoint down the lowest because that's not included. Does that make any sense? Okay, you'll never get an absolute low point on that because remember, x could be 0.0, infinity zeros 1, right? You'll never pinpoint that down to an exact point. Does that make any sense? Okay, same thing happens here. This time you're not including either endpoint, so that means you're not going to have an absolute max and you're not going to have an absolute min. Okay, and a lot of times students want to think that that absolute max is 4. No, it isn't. Because if you plugged in 1.9 repeating 9s, you would never get 4. Okay, the only way you're going to get 4 is if you plug in a 2 and do 2 to the second. Okay, and since you're undefined there, it can't be a max. Does that make any sense? Okay, because remember, if you did like 1.9 repeating 9s forever squared, you won't get 4. You'll just get close to 4. Okay, that's the idea. Okay. Okay, so let's look a little bit at just identifying things and kind of make sure we have this part down here. Okay, so on this graph on A, tell me what the x value of the absolute max is. B. Okay, yeah, that's your absolute max. Okay, so that's at B. How about the absolute min? What's the x value there? C2. C2, good. Okay, so that is your min right there. Okay, now a couple other things I want to mention, because this is picky, but you have to understand it. This thing right here is a local max. Okay, this right here is a local min, and it's also an absolute min. Okay, but this thing right here is not a local max. How come? Because it doesn't start decreasing. Okay, remember there's got to be a local max has to be a place where it increases, hits a high point, then decreases. It's got to be something going on either side. Okay, that's how that goes. Okay, next one. Tell me what the local max is on this one. C, good. Okay, there's your max. How about the local or the absolute min? No. There isn't one. How come?
It's not included.
Not included. You'll never hit a low point. You'll get close to it, but you'll never hit it. Okay? In fact, you'll get infinitely close to it, but you'll never hit it. Okay, part C on the next page. Tell me what the absolute max is.
C?
Absolute max.
None.
Careful. None. Careful, okay? It looks like it's going to hit the high point in there, but it's a bubble, so you can't hit one.
So you wouldn't include the other one, like the one that is the highest piece that is included?
Now you got remember when you're doing an absolute max, you're looking for the absolute highest point the graph ever hits. And this point right here is not the absolute highest because you got a bunch of y values that are bigger. Okay, how about the absolute min? A. Yeah, it's got an absolute min for sure. So we got that. Okay. Okay. How about the next one? Absolute max. No. A. Okay. When you're at A, that's where your y value is. That's solid there, so that's it. Right? Solid dot means that is a definitive point on the graph. That's not there. It's not there. That point right there is clearly higher than the other two, right? Okay, how about the absolute min? C. Yeah, that's pretty clear there. That's the absolute low point, so that's C like that. So there's a lot of little details. It depends a lot. Your function can look all kinds of different ways. It doesn't have to have an absolute max or min. Okay. Okay. So this kind of think I've pretty well gone over what I want to see on here. A couple other things is like this function on A would not have an absolute min or max just because the graph goes on forever, right? Okay. Now, does this graph right here have a local max and a local min? Yeah, there's a local min there, local max there. Okay. Everybody understand the difference between the two? Okay. All right. Here's another one. This one does not have an absolute min because the graph gets lower forever. It does have an absolute max, right? And that also is a local max. Okay. right? Next one, it has no absolute max because the graph gets higher forever. Okay, it does have an absolute min because of that though, so it does hit a low point. Okay, it's not that bad. Does everybody understand what we're saying by this? Okay, you got to make sure the little picky details as you got that under control too. Okay, so let me talk a little bit about what the extreme value theorem is and kind of talk about this a little bit. I took this out of another calculus book because I wanted to mention this. It says a function that is continuous on a closed interval has an absolute value, an absolute max, and an absolute min on that interval. Okay, now here's what this says. Okay, I'll have you draw just a couple of diagrams on this. Okay, let me give you 3 examples here. Okay, now first of all, what this is saying is we're going from A to B, and we have a closed interval, and we're continuous. So if I wanted you to draw a graph that's continuous from A to B, what would you have to do? Versus discontinuous.
You'd have to squiggle it.
Well, you could if you wanted to, but the thing is there would be no place on that graph where there's a break. It would be a continuous something where you'd never lift your pencil, in other words. So let's do something like that. And let's just say it starts there. Okay, you can make it wiggle as many times as you want to, but that would be a continuous graph, right? Okay, does that have an absolute min?
Yes.
Yeah, right there. Does it have an absolute max? Yeah, right there. Okay, absolutely. So there's your max. There's your min. Okay, let's do another one. Let's say here's A, here's B. Now remember, you have to make it so it's continuous. Okay, so let's start this one off here, and then let's just do something like this. Okay, now this is a weird one. Let's say we decided to connect it with a line like that. It's continuous. Now this one's weird. Does it have an absolute max? Yeah. Every place is the same. It has an infinite number of absolute maxes because they're all the same. Does it have an absolute min? Yeah, really. Really, you can think of this as a high point and a low point at the same time. So that would have an infinite number of maxes and mins in there. Now, we're not talking about local. We're talking about absolute max and min. Okay? Now, let's do it this way. Let's say we have A. Let's say we have B. And this time, let's make it discontinuous. Okay, so there's several ways you can make something discontinuous. One way is you could say, okay, let's put a break in there somewhere. Okay, so let's say that we just did a graph that looks like that. Okay, so would that have a local, would this graph that I just drew, would that have an absolute max?
No.
No, and it's because it's discontinuous. Once you make the graph discontinuous, then it's not going to have to be guaranteed to have one or the other. Okay, now it does have absolute min. It's kind of a tie between A and B on that. But that one does not have, it has no absolute max.
So when, like, let's say, for example, when you're writing down the absolute minimum, would it be like A union B? Or?
No, what you just usually list them with the X values. That's one way. So you just say X equals A, X equals B. Or you can write them as points, like A0, B0, like that. But the point is once it's discontinuous, then it fails. Now you might have a min, but you wouldn't have the other one. It depends. Another way to draw this would be like this. You don't need to draw this on your paper, but say that you had A and B. Say that you had a vertical asymptote. Okay, then you might have a graph that does something like this. I mean, this is a possibility. Okay, does that graph have an absolute max?
No.
No. Does it have an absolute min?
No.
And what caused the problem was the discontinuity. So when you have a discontinuity, it doesn't happen. But if it's continuous, you are guaranteed to have a max and a min. You're absolute guaranteed. Okay?
So that last, that graph with that was discontinuous, the one up there.
This one?
Yeah, it doesn't follow the theorem then, right?
No. Well, it does follow the theorem, but it doesn't follow the continuity. So if you're discontinuous somewhere between A and B, then you're not going to necessarily have an absolute max or min. That's what that says. But as long as you draw it continuous, you're going to have them. You could draw all kinds of ways, but that would be the idea. So here's what this was saying, basically, is Okay, if you look at this graph right here, is that continuous?
Mm-hmm.
Yep. Does it have an absolute max?
Yep.
Yep. Does it have an absolute min?
Yes.
Yeah, so see, that's what that theorem
What
says.
if you had a horizontal asymptote? Would that be your, like, say, would it be like
Okay.
your minimum or your max?
Let me see if you're thinking this. Okay, let's say you had a horizontal asymptote like that, and let's say you were going from A to B, and you had a graph kind of going like this. You know it's going to level off, but we're stopping there. You would have an absolute min. That would be your absolute min right there. And you would have an absolute max. It'd be that. Okay, now remember the theorem says you got to go from A to B. You're not going from negative infinity to infinity. That does not apply to this theorem. Okay, that's the idea. Okay, so anyway, this one right here, the absolute max on this one occurs at A. Absolute min is at C. This does meet the conditions of the extreme value theorem because it's continuous. How about the next graph? Does it have a max, an absolute max?
Yes.
It does. Okay, it's at C. But does it have an absolute min?
No.
No. Okay. Does it follow the conditions of the theorem?
No.
No. The problem is you're discontinuous. You got a break. The other problem is your endpoints are not closed. Okay, so you have to be continuous, and you have to have closed intervals. It's got to look like that, closed and continuous. Then it works, okay? Okay, so we've already talked about critical points. I'm not going to get into that because we've already talked about that. That's just a place where the derivative is 0 or it's undefined, okay? Now we're going to go through now a couple of examples on how you actually find absolute extreme values. With calculus, without a calculator so much, so we're going to do that. So this is kind of telling you what you need to do. I'm not going to read that to you or anything. That's just for you to refer to. I'll kind of go through that as I do this example, okay? So what you need to do is you're given a graph, you're given a function, and then you're given an interval. Okay, so I'm giving you a function and an interval, and without graphing calculator or technology, we want to see if we have an absolute max or absolute min. So the first thing that you have to do is you have to really start this way. You got to ask, is this continuous on -2 to 3? Now, how do you know that? That depends on your knowledge of graphs. What is the graph of x squared minus 10? What kind of graph is that? It's a parabola. Is a parabola continuous? Does it have any breaks? Doesn't have any asymptotes, no breaks. It's defined everywhere. So the answer to that is yes. And the other thing is this a closed interval that I gave you? Is -2, 3 closed?
Yes.
Yes. Okay, so that means that the technique I'm going to show you will work. You have to verify that extreme value theorem before you even do the problem. If this was an open interval, -2 and 3, then you may not have a max or min. Or if it was discontinuous, you're just kind of wasting your time. Okay? So what we do is the second thing we do is we go ahead and find the critical points. All right, how do you find critical points? Take the first derivative, see where it's undefined or 0. So go ahead and do that. So what's the first derivative? 2x. That's an easy one. Is 2x ever undefined? No 0 denominators, nothing going on there. That's nice. So we go ahead and set it equal to 0. Okay, solve that equation. What do you get? X equals 0. Okay, so what you have is you have a critical number at x equals 0. Okay, so what you do now is, to kind of finish the problem up, is you go ahead and you evaluate the function at the endpoints. So one of the endpoints is -2, the other endpoint is 3, and you go ahead and add on that critical point like there. And then you're going to evaluate the function at the endpoints and the critical numbers, and then you're going to see which one's the biggest and which one's the smallest. And that'll give you the answer to the problem. So what we're going to do is go back to the function. Don't plug into the derivative. Don't get confused with making sign charts and stuff. So we're just going to do something squared minus 10. Okay, we're doing x squared minus 10. So you want to evaluate again, you want to plug in the endpoints, and you want to plug in the critical number. And you will get values, and then that will be able to tell us what our absolute min and max are on this problem. Okay, so this is going to give 4 minus 10, so that's negative 6. The next one is 0 minus 10, that's negative 10. And the next one's 9 minus 10, so it's negative 1. Everybody see what I'm doing? Okay, so which one of those numbers is the smallest? Okay, so that means that this right here is your absolute min. Okay, right there. That's a guarantee. Which of those three numbers, not the numbers we're testing, but these, which is the biggest? Negative 1. That is your absolute max. Okay, so what you would have here is this is your absolute max. That's the answer to the problem. You don't even have to really look at a graphing calculator. That's a guarantee. So if you look at your endpoints and evaluate all the critical numbers, that's how you answer the question, okay? So what you would say then is you would write your answer kind of like this. Now you can write this different ways. You could say, the best way to write the absolute min is just say, you can say x equals 0 if I want the x value. If I want the y value, you just say at y equals negative 10. And then for an absolute max, most of the time a textbook, when they want an absolute min or max, they want the y value. You'll have to kind of follow that when you're doing your homework on MyMathLab. Absolute max occurred at 3. X equals 3, and that's y is equal to negative 1. Okay, like that. Now, I think I put this graph on your handout. Didn't I put that on there? Okay, so this is the graph of the function. What you end up having is you might want to write a note that that point right there is the point 3, negative 1. That's your max. And then this point right here was the point 0, negative 10. That's your absolute min. It's very easy to do with technology, but you're in a calculus class, so you're trying to learn the concepts that are behind this. Okay, does that make sense? Okay, so notice that what you have on this graph, you had a closed continuous function. So if your endpoints are closed and you're continuous, you're guaranteed to have an absolute max and min. It's an absolute guarantee. And if they occur, they're going to either occur at the endpoints or the critical point. And the critical point on that is where the tangent line is horizontal. That's it. Okay, does that make sense? Tell me. I have no clue. Makes sense to me. Okay, all right. Okay, let's do one more, then we'll take a break. I'm not going to do too many of these because you follow the directions on here, you're going to do the same things kind of over and over again. So here's a different function. Okay, so I'm given this function and I'm given this. So the first thing that you have to ask yourself is this function continuous? Well, what this function really is if you have a 4/3 power, it's really saying that g of x is equal to the third root of x plus 1 to the 4/3. No. I'm sorry, the fourth power. It's a third root of that to the fourth power. Let me fix that. Okay, so let's say that you don't have a calculator. I mean, if you look at my graph, it's clearly continuous. But here's what I want to see if you guys understand. Okay, can you take a cube root of any number? Or are there numbers that you can't take cube roots of? You take a cube root of anything. Can you take a cube root of a negative number? Yeah, that's why I'm asking, because a lot of times students don't know that. If you had the cube root of negative 8, that's negative 2. The reason is because if you multiplied negative 2 out 3 times, you get negative 8. Don't confuse that with a square root. So it's continuous, okay? The other question you have to ask is this interval I gave you, is that closed? Yes, it's got brackets. If it had a parenthesis, the whole thing would fail, okay? Even if there was a parenthesis on 1. So that means that we can proceed with the problem. If either of those conditions fail, you can't even proceed with the problem using this methodology. So what we're going to do is we're going to go ahead and do the first derivative to find our critical numbers. Now this is a chain rule, so you're going to bring down the 4/3. That's x plus 1, then you're going to subtract 1 from the exponent. So if you're doing 4/3 minus 3/3, that's 1/3. Then you got to do the derivative of what's inside, which is what? 1, okay? So that means your first derivative is g prime of x is equal to 4/3 x plus 1 to the 1/3. Okay, like that. Now I'm going to go ahead and write that as 4/3. Let's go ahead and write that as the third root of x plus 1. A 1/3 power is a cube root. It's the same thing. Okay? So now, what you want to do is you want to set that equal to 0. And then we want to solve this equation. So we have 4/3 cube root of x plus 1 equals 0. Okay? Now, how do you solve an equation like this? Well, you have a fraction. So one way to do this is just make this 4/3 go away. Okay? You could multiply by 3, or you could even multiply by 3/4, both sides. That just gets that whole fraction to go away. If you do that, you're going to have, that's just 1, right? That's 12 over 12, that's 1. So you've got the cube root of x plus 1 equals 0. Okay? Well, the way you do this is, and this gets into algebra background issues. Before I do this, let me ask you if you guys know how to do this. What if you had square root of x plus 1 equals 0? How do you solve that equation? You square both sides. See, that's algebra background stuff. And that takes the radical off, then you could solve from there. Okay, well, how do you get rid of a cube root? You cube both sides. Okay, so you want to raise both sides to the third power. Okay, that's going to leave you with x plus 1. 0 to the third is 0. So what's the answer to that equation? -1. So that's your critical number, as you have that then. Okay, now see, that's algebra stuff. We haven't solved a lot of equations with radicals, but you're going to do that from time to time. That's the general thing, is square a square root, cube a cube root, and so forth. You get rid of it. Okay, so the third thing you do is you want to look at, we only have one critical number, so you want to go back and do g of -9. That's an endpoint. You want to do g of -1. See, that's the critical number. And then you want to do g of 7. Okay, we know that the max and min's either going to occur at a critical number or an endpoint. That's what we know. So what we're going to do is, when you evaluate these, go back to the function. So we're going to do this. We're going to go back to the original function. We're going to do -9 plus 1 to the 4/3. We're going to do that without a calculator too. I mean, you can do it with a calculator, but you need to know how to do this without a calculator. And then I'm going to do -1 plus 1 to the 4/3, and then 7 plus 1 to the, that should be a 4/3. Okay, like that. Okay, let me show you how you do this without a calculator. So here's what you do. This would be -8 to the 4/3. What that means is that is a cube root of -8 all to the 4th power. You rewrite that like that. Okay, we've learned how to rearrange exponents and radicals. Okay, what is the cube root of -8? I did that a minute ago. That's -2. Now if you take -2 to the 4th, that would mean multiply -2 out 4 times, you would get positive 16. Okay? Okay, the next one, you have -1 plus 1, so that is 0 to the 4/3. Well, that really is cube root of 0 all to the 4th. Okay, what's the cube root of 0? 0. What's 0 to the 4th? 0. Okay, you got that. Okay, do the next one. 7 plus 1 is 8, so that's 8 to the 4/3. What that really is the cube root of 8 to the 4th power. Okay, what's the cube root of 8? 2. 2 to the 4th? 16. Okay, you can certainly use your calculator, but I would certainly like a student to be able to do that without having to do a calculator too. Okay, all right, because you need to know the math behind that. So, what is the smallest? Okay, so what is this? That is your absolute min. Okay, so there's your absolute min. What's the biggest? It's a tie. Okay, so you do have two absolute maxes. You can have more than one. If it's a tie, you got to use both of them. Okay? So the way you would write your answer is like this. You would say absolute max. Usually the way our textbook likes you to do this is say absolute max is 16 at x equals -8. No, -9. You got to look at the x value, -9, and x equals 7. So it's at the endpoints. Then you would say we have an absolute min at, that value is 0, and it happens when x is equal to -1. Okay, these problems are super easy to verify in your calculator. It's just, there's your absolute minimum. That happened at -1, 0. There's your max. It happened at the endpoint. So you might want to write a little note to yourself. This is 7/16. This point over here is -9/16. And this point right here is -1, 0. So since you're learning calculus, that's why we're doing it with calculus, to help you understand the concepts. Okay, that's the idea. Okay, it's easy to check on your calculator for sure, but that's what you do. Got to go through a 3-step process when you do that, okay? All right, let's go ahead and do a break here for 10 minutes. Okay, so let's look at the physics here. Okay, let's go through this example right here. So this one is saying that you have, in physics, you have, anytime an object is thrown, it follows a path of a parabola. Any projectile on Earth follows a parabolic path. Okay, I'm giving you the quadratic function that's given. I'm giving you a closed interval. That's pretty important. Okay, and then what we're going to do is we're going to find when the stone reaches its maximum height. So we're going to do this by finding an absolute max and min. Okay, so we're just going to follow the same procedure we just did. We're just attaching this to some application. Okay, the first thing is you want to ask yourself 2 questions. Is the function I gave you continuous? And is it a closed interval? That's important. So is that function continuous that I gave you?
Yes.
Yeah, it's a quadratic. It's a parabola. There's no breaks. So that's a yes. How about the interval? Is that closed?
Yes.
Yes, okay. It's got less than or equal to. That's really the interval 0 to 6. So it is closed. So that means we can proceed with the 3 steps we're doing. Next thing is find critical numbers. So what do you need to do? First derivative, set equal to 0. Good, okay? So the first derivative would be s prime of t. S is representing the height of the object. That's an easy derivative. What's the derivative? Negative 32t plus 64. Good. Okay, like that. Okay, now we're going to set that equal to 0. So we're going to have negative 32t plus 64 equals 0. Well, I'm just going to solve for t. I'm going to move the t the other side. The best way to do this is probably just have 64 equals 32t. Then you can divide by 32. So it looks like 2 would be your critical number. Okay, so what you have is you have a critical number at t is equal to 2. Okay, now what we're going to do on this is we're going to go ahead and follow the procedure that we did. So what we're going to do is in step 3, you want to do the endpoints, 0, s of 0, you want to work that out. You want to do the other endpoint, 6, and then the critical number. Now, one thing I haven't mentioned yet, but this could happen from time to time, if your critical number was not within the interval 0 to 6, you wouldn't even mess with it. So like if I got a critical number of 8, then you wouldn't even do it, okay? Because it's got that critical number has to be between the endpoints and the interval. Does that make sense? Otherwise, it'd be, get a wrong answer, okay? So what we're going to do with this one is just evaluate. So let's start with 0. We have negative 16 times 0 to the second plus 64 times 0. You could certainly use your calculator on this if you wanted to. That'll give 192. Okay, if I go to the next one, that is negative 16 times 2 to the second, 64 times 2 plus 192. You can do that all in one step in your calculator if you want to. You can even graph and get this with your graphing if you want to. Okay, so I'm going to go ahead and get that worked out. So that's really negative 16 times 4, 2 to the second's 4, 64 times 2, and then plus 192. I suspect this is where the max is. Okay, so that's 256. Okay, then do the 6. So you'll have negative 16 times 6 to the second plus 64 times 6 plus 192. So let's do that. So that'll be negative 16. 6 to the second is 36 plus 64 times 6 and then plus 192. And let's record what that is. So that's back to 0. Okay, like that. Okay, so you're back to the ground. You've hit the ground is what's happened there. Okay, so what is the absolute max? Yeah, 256. Okay, so right there is your answer. So what you would say on that is you would just say, usually we say absolute max of 256 at x equals 2 seconds. Okay, now that's time is in seconds. So that's usually, I think, the way that they want you to write this. Sometimes a textbook will have you say f of 2 equals 256. On a test, I usually will specify maybe I want a point, maybe I want the y value, maybe I want the x value. Okay, that's the idea. Okay? Does that look okay to everybody? Okay? All right. Let's do a little quick check on the calculator with this one, and then we'll finish up with that last one. Then we're going to get into the next section a little bit here. So again, when you're doing your homework, do the calculus, and then you probably ought to turn around and just, as many of these as you can, graph them, and verify your answer that way. So I'm going to put in negative, let's see, where's my function? I'm going to put in negative 16. I got to put an x in. So I'll have x to the second. Whoop, got to put the x in first. Let's see, negative 16 x to the second, and what was it, plus 64x, and then plus 192. Now, okay, now on a window, let's do a window like this. Okay, we're only going to go to 0 to 6, because that was given in the problem. That's your closed interval. So I'm going to scale by 1. Okay, and the biggest value was 256. I'm going to maybe make that go, that's the absolute max, so let's just maybe make y go from 0 to 300. Okay, then maybe scale that by 10. Now, I'm not going to have you draw a graph, I just want to show this to you. So, okay, so that's kind of what your graph looks like. You can easily verify this just by doing this. You can trace at 2, and then notice that's blinking at the max, and then there's your 256. So it's real easy on your calculator to tell you right. Okay, everybody with me there? Okay, we've been doing a lot of these steps with max and min, so it ought to be starting to sink in pretty good. Let's do one with a revenue. So this time I've given you the revenue function, and I'm giving you an interval 0 to 5. So we're going to find the critical points, then we're going to find the absolute max on this then, okay? So the first question is the function continuous, the revenue I gave you, and is the interval closed? So are those yeses or nos?
Yes.
Okay. All right, so yeah, we have a continuous function. We're doing quadratics. That's what you're going to work with mostly. And yeah, you do have a closed interval. Okay. So we're going to go ahead and do the critical points. So do your first derivative. That should be pretty simple. R prime of x, what's the derivative? That looks like negative 120x plus 300. Okay. Set it equal to 0. So that's negative 120x plus 300 equals 0. Solve that for x. You may get a decimal. I'm going to move the x to the other side. Doesn't matter what side you get x on. Okay, I can divide by 120. And then let's just do our calculator and see what that is then. I think that's got a 0.5 on it, doesn't it, or something. Okay, so let's see, that would be a critical number, and you want to make sure that that's between 0 and 5. So 300 divided by 120 looks like 2.5. So that would be your critical number would just be at 2.5. Okay? All right, now what we do is we evaluate the revenue at 0, we evaluate the revenue at 2.5, and we evaluate the revenue at 5. Now see, what I'm going to do on this, you can save a little bit of time, and when you do a test, you can use your calculator. It's not a bad idea to just go ahead and graph it and then trace those numbers. So what I'm going to do this time is I'm just going to put in the function negative 60x to the second, and then plus 300x, and I'm going to set up a window on that. Now the graph says go 0 to 5, so I'm going to do a window from 0 to 5. What you can do on this is, again, for your y, just look at your table. So if you go second graph to open up your table of values, you can pretty well see the biggest value I'm seeing is 360 in there, because we're only going to 0 to 5. So for that reason, I'm going to choose to make the y's on this problem go 0 to 400. And then scale it like that. Okay? And see, you can do it this way. This way you're checking and getting the function values at the same time. So there's my window. If I graph it, now what I'm going to do to save time is just trace out these values. So I'm going to go trace 0, and that's going to give 0. You always expect a revenue at 0 to be 0. Then we can trace at 2.5 on the calculator, and that'll give 375. And then we can trace at 5 and get 0. So see, by doing that, you're kind of checking your work and you're getting those values at the same time. So clearly your absolute max occurs there. Okay, that's your answer. 375 is your absolute max. Okay? All right, does that make sense to everybody? Okay, so when you're doing these problems, be sure that you evaluate the endpoints and the critical numbers. And you find which one's the biggest and which one's the low. The absolute min would be 0.
So then you would put like absolute max of $375 at 2.
Yeah, the standard way is just say 375 at 2.5. X equals 2.5. Okay. Okay, and that's a pretty short section. Everything you're doing is pretty similar to that. It's just kind of got one major concept in it. Okay, so let me go ahead and give you this 2.6. We're going to probably do we don't have time to do the whole thing, but we're going to do some of this today. And this is where you get into what's called an optimization problem. We're going to do different types of problems here. Get everything done. Okay, I'll have it graded before class because I got the rest of it done last night, so I'll get it. Okay.